In the annals of space exploration, few missions have captured the imagination quite like Voyager 2. Launched in 1977, this intrepid spacecraft embarked on a grand tour of our solar system's outer planets. Its primary mission was to study Jupiter, Saturn, Uranus, and Neptune, gas giants shrouded in mystery. These distant worlds, with their swirling atmospheres and enigmatic moons, beckoned with the promise of groundbreaking discoveries. Voyager 2's journey was a testament to human ingenuity and our insatiable thirst for knowledge. The spacecraft carried an array of scientific instruments, including cameras, spectrometers, and magnetometers. These tools would allow scientists to study the planet's atmospheres, magnetic fields, and rings in unprecedented detail. Voyager 2's journey was about more than just scientific exploration. It was a journey into the unknown, a quest to unravel the secrets of our celestial neighborhood. The mission's success hinged on a complex series of flybys, utilizing the gravitational pull of each planet to slingshot the spacecraft towards its next target. This gravity assist technique not only saved time but also conserved precious fuel, enabling Voyager 2 to venture farther into the cosmos than initially planned. As the spacecraft hurtled through the vast emptiness of space, it beamed back a treasure trove of data that revolutionized our understanding of the outer solar system. Voyager 2's first encounter was with Jupiter in 1979. The spacecraft captured stunning images of the gas giant's swirling clouds and discovered 3 new moons. Next came Saturn in 1981, where Voyager 2 revealed the intricate structure of the planet's rings and provided close-up views of its largest moon, Titan. Each planetary encounter brought new revelations, pushing the boundaries of our understanding. Voyager 2's cameras captured images of volcanic activity on Jupiter's moon Io, a phenomenon never before observed beyond Earth. The spacecraft's instruments also detected lightning strikes in Saturn's atmosphere, hinting at the complex weather patterns on this distant world. With each flyby, Voyager 2 painted a more vivid picture of the outer solar system, showcasing its diversity and grandeur. The data beamed back from Voyager 2 not only provided valuable scientific insights, but also sparked public imagination. These distant worlds, once mere points of light in our telescopes, were now revealed in all their glory. The mission ignited a passion for space exploration that continues to this day. Voyager 2's encounters with Jupiter and Saturn were remarkable, but it was the spacecraft's visit to Uranus in 1986 that truly captivated the world. Uranus, the 7th planet from the Sun, is an ice giant, a world vastly different from the gas giants Jupiter and Saturn. Its atmosphere, composed primarily of hydrogen and helium, is tinted a pale blue-green by the presence of methane. One of the most intriguing discoveries made by Voyager 2 was that Uranus's magnetic field is tilted at a dramatic angle compared to its axis of rotation. This unusual orientation suggests that the planet's magnetic field is generated by a process different from that of Earth or other planets in our solar system. The spacecraft also detected 10 new moons orbiting Uranus, each with its own unique characteristics. Voyager 2's flyby of Uranus provided a wealth of information about this mysterious world. It revealed a planet of surprising complexity, with a dynamic atmosphere, a tilted magnetic field, and a system of intriguing moons. The tilted magnetic field of Uranus is one of the most perplexing mysteries uncovered by Voyager 2. On Earth, the magnetic field is generated by the planet's molten iron core. Uranus, however, has a relatively small, solid core. Scientists believe that the planet's magnetic field may be generated by a layer of electrically conductive fluid located at a shallower depth. This fluid layer, likely composed of water, methane, and ammonia, could create electric currents as the planet rotates. These currents, in turn, would generate the planet's off-kilter magnetic field. The exact mechanism, however, remains a subject of ongoing research. Another mystery surrounding Uranus is the strange behavior of its moons. Some of Uranus's moons, including Miranda and Ariel, show evidence of intense geological activity in their past. These moons are crisscrossed by canyons, fault lines, and other features that suggest they were once much more geologically active than they are today. Scientists speculate that tidal forces from Uranus may have played a role in heating these moons' interiors, leading to the observed geological features. The curious case of Uranus's magnetic field. Voyager 2's flyby of Uranus was brief, lasting only a few hours. Yet, in that short time, the spacecraft gathered a wealth of data that continues to intrigue scientists to this day. One of the most puzzling findings was the discovery that Uranus's magnetic field is constantly bombarded by the solar wind, a stream of charged particles emanating from the sun. This interaction creates a magnetotail, a long trailing region of magnetic field lines that stretches far behind the planet. However, unlike the magnetotails of other planets, Uranus's magnetotail is twisted into a complex, corkscrew-like shape. This unusual configuration is thought to be caused by the combination of Uranus's tilted magnetic field and its rapid rotation. The solar wind's impact on Uranus's magnetic field has profound implications for the planet's atmosphere. Charged particles from the solar wind can erode Uranus's atmosphere over time, stripping away its lighter elements, such as hydrogen and helium. This process could explain why Uranus's atmosphere is less massive than that of its neighbor Neptune, despite the two planets being similar in size. New discoveries from old data. Decades after Voyager 2's encounter with Uranus, scientists continue to analyze the data transmitted back from the spacecraft. Advancements in computer processing power and data analysis techniques have allowed researchers to extract new insights from the aging datasets. Recently, a team of scientists reanalyzed Voyager 2's magnetic field data from the Uranus flyby. Their findings suggest that Uranus's magnetic field may be even more complex than previously thought. The team identified what appear to be plasmoids, giant bubbles of plasma, being pinched off from the planet's magnetotail. These plasmoids, which have never before been observed at Uranus, could be carrying away significant amounts of the planet's atmosphere. The reanalysis of Voyager 2's data highlights the enduring value of space exploration missions. Even decades after their completion, these missions can continue to yield new discoveries as our ability to analyze their data improves. Voyager 2's legacy is a testament to the power of long-term scientific inquiry. Implications for Titania and Oberon. The discovery of plasmoids escaping from Uranus's magnetotail has implications for our understanding of the planet's moons. Titania and Oberon, the two largest moons of Uranus, orbit within the planet's magnetosphere. If plasmoids are indeed carrying away significant amounts of Uranus's atmosphere, these moons could be directly impacted. The plasmoids could deposit material from Uranus's atmosphere onto the surfaces of Titania and Oberon, potentially altering their composition. Moreover, the interaction of these moons with the plasmoids could generate auroras in their atmospheres. These auroras, while visually stunning, could also provide clues about the composition and dynamics of the moon's atmospheres. The potential for atmospheric exchange between Uranus and its moons underscores the interconnectedness of planetary systems. Processes occurring on a planet can have far-reaching effects on its satellites. Magnetic fields. Guardians of life? The study of planetary magnetic fields has taken on new significance in recent years, as scientists increasingly recognize the important role these fields play in protecting planets from the harsh realities of space. Earth's magnetic field, for instance, acts as a shield, deflecting the solar wind and preventing it from stripping away our planet's atmosphere. This protective barrier is considered to be one of the key factors that has allowed life to flourish on our planet. Without a magnetic field, Earth would be a much harsher and less hospitable place. The discovery of planets with their own magnetic fields is therefore of great interest to astrobiologists, who are searching for signs of life beyond our solar system. A planet with a strong magnetic field is more likely to have retained its atmosphere, making it a more promising candidate for hosting life as we know it.